With Thermo Video 8, we're getting into entropy. So we have wrapped up enthalpy, the heat of reaction, and now we're looking at the randomness of our system, or the disorder of the system. And you saw the definition on the first page, and here I have it a couple different ways, using the words disorder, using the word randomness, and then the dispersal of energy. But really you want to think of entropy as disorder. And we can look at this conceptually or mathematically. Conceptually, it's just how random things are. If you're comparing one place to another one, which one is more randomly arranged. But there is a mathematical way to look at this, and it has to do with a concept called microstates, or possible arrangements of particles, which is what this is showing. This is showing if we had 4 different particles that were in 2 different chambers, all the different ways they could be arranged. All of them on one side, all of them on the other side, all the different versions of 3 and 1, 2 and 2, and 1 and 2, or 1 and 3. Those would all be different microstates, and we could solve for entropy, which is S, by using an equation S equals K times the natural log of W, with W being the microstates. Not something you're ever going to have to know, but I do want you to know there's an equation and know that the term microstate has to do with each different arrangement. So the second law of thermodynamics says the entropy of the universe increases in spontaneous processes and in equilibrium processes is unchanged, or reactions are spontaneous or occur on their own when entropy increases. So total entropy would be the entropy of the universe. So that means the entropy of the system we're looking at and its surroundings when that is greater than 0, when we are increasing the overall disorder by either increasing the system or increasing the surroundings or both, such that our total increase of disorder is positive, it's spontaneous. And what spontaneous means is that it will happen on its own, and the word now used by the College Board is thermodynamically favorable. The reason they changed the word spontaneous for thermodynamically favorable is we think of spontaneous as happening quickly, but that's not what it really means. It just means happening on its own. So a diamond will turn into graphite spontaneously, meaning thermodynamically favorably. We're increasing the disorder when that happens, but it takes thousands of years for it to happen. And although there will be a lot of crossover from one topic to the next, stoic to thermo to kinetics to equilibrium, it's important to keep in mind that some things are unrelated to others. So the speed of this and any reaction is only a topic for study in kinetics, and it doesn't affect whether it's endo or exothermic, whether the entropy is increasing or decreasing, free energy, any of those other things. So when we talk about this, there's a couple different ways we will look at entropy, and it's all about, once again, disorder. So you think of entropy as disorder. The standard entropy is the absolute entropy, or the value of how much disorder there is under lab conditions, so that 1 atmosphere and 25 Celsius. So gases have the most entropy. They have more than solids because the particles are moving randomly. As your molecule becomes more complex, there's more possible microstates or more different ways to arrange it, more disorder. And the heavier atoms have more disorder or more entropy than lighter atoms. And the important thing here is that's not about mass. It's because you have more electrons. And electrons are things that are constantly in random motion. With hydrogen only having 1 compared to something like mercury that has 80, those 80 electrons are much more randomly arranged than the 1. So it is very common to think of it in terms of heavy versus light or atomic number, but it's really the electrons that are the major contributing factor to the amount of entropy, because the change in the disorder of the nucleus is very little as you're adding protons and neutrons in. They're still packed as tightly together as they can be in very, very small volume, but the extra electrons are what's moving randomly and taking the space. So you could be asked about one thing by itself, why does it have this much entropy? Or you could be asking, during a chemical reaction, what happens to the entropy? So we are changing. When we go from one thing to another, is our entropy increasing or decreasing? And we've got sample problems with each of these. But increases in entropy, the favorable process, the positive delta S, which means more disorder, means we take something that has very few moles of reactants and we break that down so that there's more moles of products. So you can count however many moles of reactants and the moles of products. If there's more on the right side, that is an increase in disorder. If solids and liquids turn into gases, that's going to be more disorder, more spread out. If a solid solute, which is nice and orderly in a crystal lattice, dissolves in the solvent or water, now it's more spread out and more random. There are a few ions that, because they attract water molecules so strongly, even when they break apart, the entropy decreases. But that's not something you necessarily have to memorize. But if you're told this decreases the entropy, what you would think about is we have less disorder, and it would be about that solvation process. That is what's making it more ordered. If you have something like CO2 that is dissolved in water in a carbonated beverage, when the gas gets out of solution, now it's more randomly moving, so that's an increase. Or when you add heat, the particles start moving more quickly. When they start moving more, they start moving more randomly. So all of those are increases in entropy. All of those are kind of the natural flow or the spontaneous or favorable way. To decrease entropy, we have to somehow force that. There has to be something paired with it that allows that to happen. So if the opposite of any of these are occurring, it's because there is something else. Our surroundings must be increasing in entropy so much that our system can decrease in entropy. And as we look at the system and the surroundings here, so I've got this equation up here and this new one down here, I said that here we are talking about all increases, which are good. This is decreases, which is negative, or the unfavorable one, the forced one. So it's important that we understand how we could change the entropy of the surroundings. The surroundings are not what we are studying, so there's not much that we care about or know about there. But we do know that if the surroundings, whatever they are, whether they're a liquid, whether they're a gas, whether they're a solid, when they absorb heat, the particles start moving faster and moving more randomly. So exothermic reactions, things that release heat, if the system gives heat to the surroundings, it always increases the entropy of the surroundings, and endothermic does the opposite. So we've got an equation down here, not one that you're given, that has to do with this. So if this has a negative sign, we've got a negative and a negative. So in exothermic, our negative, negative, that's a positive entropy change for the surroundings. So the surroundings become more random. When this is endothermic and this is positive, positive, negative, makes our surroundings lose or decrease in entropy because they're cooling down and the particles are moving more slowly. The reason that temperature is a part of this equation is if it's really, really cold already, if this T value is very small, when we release heat, even a small amount of heat would have a bigger effect. But if it's already really, really, really hot out and we put just that same amount of heat out there, well, it's not going to speed up the particles that much more. The idea here is the difference between like whispering in a library. Well, if we're releasing that sound or that energy in some place where there isn't very much energy, people can hear it or it has an effect. But if you're at a loud concert or in a stadium and you whisper, you give off just a tiny amount of energy because there's already so much energy there. Yes, you are contributing to it, but it has much less of an effect. So this is not necessarily an equation that you'll be using mathematically. It's conceptually good. It's not given, but this is what allows us to think about if I had a process that decreased in entropy, how could it still be favorable? Well, it could be favorable if the surroundings increase, and thinking about what must be true about the enthalpy and the temperature for the surroundings to increase. The first two examples here have to do with first just the standard entropy value, comparing one object to another, which one is more disordered, and then looking at changes. How does the disorder change? So it tells you over here on the right, you're going to see the answers there, but which one has a higher standard entropy? I don't have the justifications written. So on A, it says that lead has a higher standard entropy. The reason there, both of these are solids, both of these are individual elements, so we're not dealing with bonded things, we're not dealing with complexity there. What happens is that lead has 82 electrons per atom, whereas the graphite, which is carbon, only has 6. So those 82 electrons move much, much, much more randomly, and as a result have a higher entropy. When we're comparing cesium solid to cesium liquid, just a side note, that does not mean aqueous cesium ions. People tend to forget that you can take anything and have it in all 3 common states of matter. So we could take something like a diamond and melt it. You'd have to get it to 6,000 degrees Celsius for that to happen, but it can be done. Or we could take helium, which is a gas, and cool it down and make it liquid, or cool it even more and make it a solid. So cesium liquid is cesium in the liquid state. That's more disordered, because even though have similar complexity, they have the same number of electrons, liquids have freely moving particles, so that is more randomly arranged. Ammonia and neon. Ammonia is our more disordered thing. Neon, it's just one individual atom or one individual element with a certain arrangement. But in the ammonia, we have a bunch of bonds. So those bonds can be vibrating. The hydrogens can be moving, kind of twisting those bonds and arranging it in so many more ways than just the individual atom. And then the next examples, that to an even higher degree, we have CH3OH, C2H5OH. Both of those are liquids, so same state. Here we have 2 things. We have a more complex molecule because there's more atoms, more bonds, so more torsions and bending and twisting. But we also just have more atoms, so more electrons as well. In both of those support more entropy or more randomness. So we have some examples of each thing where you're comparing what is similar and what's different. The first one, same state, still individual atoms, more electrons. The second one was different states, even though same electrons and same element. The third one, same state, but more complexity in the molecule, but they actually have very similar number of electrons. They both have 10 electrons. But it's those bonding and the twisting and turning and the movement of the atoms around one another that make it more complex. And then the last one, both liquids, but we have a complex molecule and more electrons. Example 15 has 5 either chemical or physical changes here in terms of increasing or decreasing the entropy. So is delta S positive or negative? And remember that delta S being positive equals more disordered. So copper carbonate to copper oxide and CO2, that is an increase in entropy. One thing turns into 2, but also something that's a solid turns into a solid and a gas. Both of those would be more disordered. So this is something that you will have to do, and you'll see very commonly, justify your choice in terms of this. So it increases, and you're thinking in terms of number of particles, the states, what's happening to the temperature, and then how our solute and solvent are mixed. B, SO2 and O2 make SO3. That decreases. They're all in the gaseous state, but we have 3 moles of gas becoming 2 moles of gas. It's becoming more ordered. So instead of all of those things randomly moving around each other, there's a little bit more, I guess, structure or more order in the system. On C, the precipitation upon mixing 2 aqueous solutions. We have aqueous solutions, ions floating all over the place randomly. They precipitate, so we are decreasing the disorder because ions that used to be freely moving around are now being locked in place in a crystal lattice. Less disorder. We know where more things are, or we could say fewer microstates because some of the things are now arranged in a certain way. There's not as many different possible ways, for the particles to float around. Water freezing, liquid to solid, that is a decrease. It's a physical change, but our freely moving particles are locked more in place. Barium hydroxide solid, ammonium chloride solid makes ammonia gas, water, and barium chloride aqueous. That's definitely an increase. We have 3 moles of reactants, we have 5 moles of products. We have 2 solids on the reactant sides, we have gases, liquids, and aqueous components on the product side. All of those things, gases, liquids, and aqueous, have more entropy than solids. So we definitely have a big increase there. So examples 14 and 15 were how to deal with this conceptually, what's happening. We have an equation here and then an example. This equation should look similar to something you've already seen, look familiar. And this is how we deal mathematically with the entropy changes. So it's not just looking at the microstates, the equation I mentioned before. It is using the entropy of formation of our products, the entropy of our reactants, finding the difference between them. This is given, so you need to know that. So just like the equivalent equation in enthalpy is given, it's the same one here, used in the same way. The only thing that's subtly or slightly different here is the unit. Just like we looked at the equation, the delta S is H over delta T. There is a temperature component to this. At different temperatures, the randomness is different. If we heat something up, if we cool it down, we are giving the particles more or less energy, which means they're moving more or less randomly. And in one of the next videos, we'll see how temperature actually does come into play in some calculations. But right here, this calculation's almost identical to things we've already done. So zoom in, I'll zoom even a little more over here. We've got a reaction, carbon and hydrogen and water make, I believe that's ethanol. So we'll do our products minus our reactants. And as we look at the values here, we can kind of see some things that we've already talked about. But delta S is equal to products, 160.7 minus reactants, 2 times 5.74 plus 2 times 130.6 plus 69.9, and that's it. All of those together add up, zoom a little bit here, those add up to the value we get right there, negative 189. So we have a big decrease in entropy. We used to be much more random than we are now. 5 separate particles into 1. And some things I want to point out before moving on is just the values here. Carbon is a solid. It has the lowest value. The ethanol has the highest value, and we can see that it's much more than anything else. Well, there it has all of those atoms bonded together that can be arranged in all sorts of different ways, with the bonds pushing and pulling and twisting and vibrating. The other thing that's really high is hydrogen, which is a gas. So we have a lot of entropy here. The liquid's kind of in between, the solid being the largest, but here our complex molecule in the liquid state having a pretty high entropy. And that leads us into, with the carbon and hydrogens, into the third law of thermodynamics, the last thing dealing with entropy on this video. It says the entropy of a perfect crystalline substance is 0 at absolute 0. Delta H, the enthalpy, was 0 for elements because to form oxygen out of oxygen took no energy. When we get into Gibbs free energy, which is the next thing, the delta G is 0. It does not take any energy to make an element out of itself, but we're not talking about making elements out of themselves. We're not talking about the energy associated with them. We're talking about how much disorder something has. And even though this is pure carbon right here and this is pure hydrogen, there are still electrons moving around. They have some disorder. So you're almost never going to see something with 0 entropy because everything has electrons in motion. The only time that your entropy would be 0 is if you've got that perfect crystal at the coldest possible temperature, and that means that you only have one microstate. Nothing is moving, and the natural log of 1 is 0, so mathematically that proves that we have no entropy. You won't really need to do any proving of that, but if you're asked to explain something along these lines, why the delta H is 0, but why the delta S of formation isn't 0, well, we have electrons still randomly moving in this solid, so we still have some disorder. So that's the basics of entropy. We'll start applying that a little bit more in our next video.